What we're going to be talking about today is we're going to be talking about something called transitive closure. And this continues our work on relations and also graphs. It's going to build on that idea of graph powers that we talked about inside of our last lecture. And I'll include the video for graph powers inside of the notes just in case you want to go over that again. The idea of transitive closure is this. Let's imagine that you have, say for example, a set of cell phone towers. Okay, and you want to know how far or to how many different places can we get utilizing those cell phone towers. Now, on the one hand, if we have one cell phone tower connected to another cell phone tower directly, we know that we can get between those two cell phone towers. But what if I can get between cell phone tower 1 and cell phone tower 2, and cell phone tower 2 and cell phone tower 3? And so if I went 1 to 2 and 2 to 3, that would be another place that I could get to from 1. Now that would be what we consider to be a walk of length 2. On the one hand, the first walk 1 to 2 and the second one 2 to 3, those are walks of length 1. But that next one, 1 to 2, 2 to 3, is a walk of length 2, if you want to think about it that way. What we're going to do with the transitive closure is let's just imagine that we can create any set of walks. Right? We can go 1 to 2, 2 to 3. If we could go to 3 to 4, we could do that. If we could do 3 to 5, we could try it that way. And so we're going to generate all of the different ones of those places that we can get to utilizing walks of any length. And so what we'll imagine is if you started anywhere in that cell phone grid and you wanted to go to any other place, could you actually do that utilizing the particular relationships between the towers? That's going to be the idea that we get here with transitive closure, where our graphs are a set of vertices that represent the towers and our edges represent the relationship between any two of our vertices. How do I find the transitive closure of a graph G? First, I want to review what are graph powers. So a graph power, G to the K, is going to be the set of all walks of length K that we can create using a particular graph G. So G squared is going to be the set of all walks of length 2 that we can create from a graph G. G to the K is going to be the composition of G with itself K times. If we want to think about G squared as, say for example, G composed with G, or think about it in terms of relations. So to give you an example, let's say for example I have this graph G, and it's made up of the self loop AA, and then it has AB and BC, and we want to figure out what G squared is. Now what G squared is going to be is it's going to be all the walks of length 2. So I'll take a walk of length 1, A to A, and then a second A to A again, and that's a walk of length 2, so A to A is inside of G squared. If I take A to A and then A to B, I end up at A to B, so A to B is also a walk of length 2, the self loop with A to B. Also A to B and B to C is a walk of length 2, so A to C is included as well. Notice none of our walks of length 2 start at B because B only goes to C and C goes to nothing. Same thing with C because nothing comes out of C, so consequently we can't generate a walk of any length from C. Now that we understand a little bit more about graph powers, let's talk about unioning graph powers. Let's say for example I have G and I have G squared, and those are our edge sets. G union G2 is going to be the set of all walks of length 1 and walks of length 2 that I can generate from G. So what I do is I just take the edges that are in G and G squared and union them together. So basically get rid of all of the redundant pieces. And how we can visualize this, or we can think about it, is that G union G2 is everything that we can get to from anywhere on G utilizing either a walk of length 1 or a walk of length 2. The graph now is going to look like this. It's going to have the self loop for A, it'll have A to B, it'll have A to C, and it'll have B to C. So essentially when we generate G union G2, or G squared, all we're going to do is we're going to represent each one of these walks as a single edge. Now that we have the idea of a graph power, and we have the idea of the union of graphs, what we're going to get is this idea of the transitive closure. So the transitive closure for G is going to be this thing G+. And G+ is the unioning of all of the graph powers of G. Literally, or theoretically, it's an infinite union of these graphs. And it's for K greater than or equal to 1. However, we don't actually need to think about it from the perspective of an infinite number of graph powers. If we have a graph that has finite number of vertices, let's say for example it has n vertices, then the maximum number of graphs or graph powers that we need to generate will be n to complete the transitive closure. So for example, if I had a graph with 4 vertices, the maximum number of graphs that I would need to generate is 4. I need g squared, g cubed, and g to the 4th to get the entire transitive closure. So let's look at an example. Let's say, for example, we have g again. And so we've got g squared, and now g cubed, and the g cubed is our 3rd graph, and it's the last one that we're actually going to need, or that we know that we need. Reason why? Because we have A, B, and C. 3 vertices, so we'll need 3 graphs. We go in, we figure out, okay, g cubed is going to be all the walks of length 3. So we could do the self loop 3 times. So hence the self loop for A. We could do the self loop twice and go A to B. That would be another walk of length 3. Or we could do the self walk once, we go A to B and B to C, and that would be this walk A to C. So you'll notice that g cubed is the same as g squared. We're actually now done. In fact, once you get the same graph over and over and over again, you know that you're in fact complete with all of the different kinds of walks that you can get from a given graph G. So now let's look at G+. G+ is just going to be the union of these. So again, it'll look exactly like G union G squared. We'll have the self loop. We'll have A to B, we'll have B to C, and we'll have A to C. So we'll have G, and then we can add in this one piece here going from A to C from either G squared or G cubed. And that's the transitive closure. What if I want to create the transitive closure, but I don't want to draw the graphs? Because drawing those graphs can be quite time consuming and sometimes a little bit confusing. Well, I can actually find the transitive closure from edge sets. And so what I'm going to do is I've got this process where I'm going to begin with the edge set for G, and then it's that edge set E. Now, I've got V as my set of vertices. It goes A through E. So the maximum number of times that I'm going to have to do this is 5 times. What I'm going to do is I'm going to find all the transitive relations from E, and anytime I come up with a new edge, I'm going to add that edge to my overall transitive closure set. So for example, I have A to B and B to A, and so that gives me A to A. And I'll note that in E, I don't have A to A. Great, so that gets added to the set. Now I'll take A to B and A to C, and I don't have A to C, and so that gets added to the set as well. Those are both walks of length 2. I take A to B, all right, B to C. So all the A to B's have all been done. So now I'm going to move on to A to D, my second edge. I say A to D and D to A. That gives me A to A. I'm done. I already have A to A already. Now I go B to A, B to A, A to B. That gives me B to B. B to A to D gives me B to D. And there we are. Now I go B to C and C to A. That gives me B to A, but I already have B to A, so I don't need to add that one to my set. I already have it. And B to C, C to C, well, I already have B to C as well. This is going to be a key piece here. Anytime I have a self loop, that self loop is actually not going to increase the number of edges that we have. Because if you kind of think about it, it's just going to go back to the one that we were already at. So consequently, when I'm going to find these transitive relations, I don't actually need to include that self loop. I can just kind of ignore that it's there. It gets included in the set, but I don't need to actually go in and check it. Now I'm going to go C to A. I got C to A, C to B, or C to A, and A to B. That gives me C to B. That's not included. Great. I got C to A to D. That gives me C to D. In addition to that, notice, remember again, we have the self loop C to C. I don't need to check C to C as a beginning self loop either, because again, it's just going to give me the same exact sets as I would have had before. Now I go D to A. So I got D to A to B. That gives me D to B. I have D to A to D. That gives me D to D. And now I'll move on to E to C. I have E to C, C to A. That gives me E to A. E to C, C to C. Don't need that one again. I have E to D now. So I have E to D, D to A. That gives me E to A. I already have E to A. Now what I'm going to do is I'm going to go in and I'm going to just check my new relations. This new set here, I don't need to go in and check E again. I'm just going to check my new ones to get all of my walks of length 3. And by the way, what I'll do is I'll go in and I'll compare all of these ones in this, call it set 1, and I'll find the transitive relations between each one of those as well, because they'll give me new walks too. So I start here, I have a self loop. I don't need the self loop, don't need the self loop B to B, don't need the self loop D to D. We're all done with those. So I'm just going to start A to C. And I go A to C, C to A. We already have A to A, we're done. How about B to B? Well, that's self loop, don't want that one. I go B to D. So I have B to D, D to A. That gives me B to A. But I already have B to A in the set. No more needed. Now I go, I'll check C to B with B to A. So that gives me C to A. I already have C to A. C to B, B to C, that's the self loop. C to D, D to A, that's already C to A. Already have that one. I have D to B. Okay. B to A, that gives me D to A. I have that. D to B, B to C, that gives me D to C. Oh, that's a new one. So that I'll put that in the set one, D to C. I have D to D. Don't need to include that one, that's fine. What about D to B? Oh, well, that kind of completes that set. How about E to A? Now I have E to A, E to B. That gives me E to B. And I have E to A, E to D. That gives me E to D, which I already had before as well. Now here's the thing. What I can do is I can actually go in and check all these ones in set 1 and create transitivity with all the other ones inside of set 1 to see if I get any new sets. So now I go A to C and C to B. That gives me A to B, which I already had before. How about A to C, C to D? That gives me A to D. I already had A to D as well. Nothing new there. How about now we take B to D, okay? B to D, and we see, oh, D to B, that's the self loop. B to D, and also a self loop, nothing else there. How about C to B? C to B and B to D, that gives me C to D. Do I have C to D? I already have C to D. Nothing there. C to D, D to B, that gives me C to B. I already have that one. And then we have D to B, D to B, D to D, nothing new. We just go in now. We're going to check E to A. So I have E to A, E to C. So we need, do we have E to C? Well, we already had E to C there as well. Okay, so all I have now from E, my first edge set, and the second set that I created is I just have these new ones, D to C and E to B. Now I'm going to do a quick check to see how many of them I actually can get out of the rest, all the other possibilities. So I've got A to A, A to B, A to C, A to D, and so the only one now that I need is A to E. And so that inevitably asks the question, can I actually get A to E? Okay, so I look here, and what things actually end in E? Do I have anything ending in E? And we notice that none of the original edges in E end in E. There are no edges that end in E that go into E, so consequently A to E is not going to be there. So there's nothing else that we can get for the A's. What about B? I have B to A, B to C, B to B, B to D, and again, I can't get to E because there's nothing going into E, only stuff coming out. So consequently, I'm done with the B's. What about C? I have C to A, C to B, C to C, C to D. I'm done with all the C's because again, there's no such thing as C to E. Or the C to E is impossible. I have D to A, D to B, D to C, D to D. We're done with all the D's. So we have everything we possibly could have there too. What about the E's? I have E to A, E to B, E to C, and E to D. And again, E to E is impossible because there's nothing coming out of E. So I can stop. I can actually stop. I have all of the transitive closure, all of these edges put together form my transitive closure that ends up being G+. So basically it's a process of elimination where we go through and we do the transitive relationships for each pair of edges and each new pair of edges that we add in until finally we can't get anything else. And every once in a while, if I've got a really large set, I want to go in and see, do I actually have everything so that I can in fact stop? And in this case, I have everything that I possibly can. I can't get any E's, so I'm done. So what about some questions about transitive closure? And again, generating the transitive closure, utilizing what we utilized before, probably not what we're going to use. We're going to use matrix multiplication and addition. However, there are some pretty simple questions that we can answer about transitive closure using its ideas. So for example, is the edge AC in G+? Well, can I generate AC? I got A to B, B to C. So yeah, AC is in G+. Is the edge DB in G+? Well, notice nothing comes out of D, and so there's no way to actually generate any graphs from D to B, so the answer is no. What is the out degree of A in G+? Well, notice that I can get A to B, I can get A to C, and I can get A to D, so the out degree there is actually 3. Notice we cannot get the self loop A because there's nothing that goes what we might want to think of as backwards. There's no way to go from, say, for example, D to C or C to B or B to A or any way to get back into A. There's no in degree to A. And so consequently, what is the in degree of A in G+? It's 0 because there's nothing going into A. So just understanding what transitive closure is allows us to answer some questions about particular vertices, okay, particular edges that might be inside of that transitive closure. So some things to remember. The transitive closure of a graph G is going to be the union of all the graph powers of G. It's the collection of all of the different walks that we can get using the edges of G. So to get the transitive closure of a graph with n vertices, we'll need at most n graph powers. This finishes this mini lecture on transitive closure. As you can see, transitive closure is actually a very powerful idea. The idea of what are all of the different kinds of walks that I can get to utilizing this set of vertices and this set of edges. What we'll do a little bit later is we're going to utilize matrices in order to envision graphs and relations, and then utilize matrix multiplication and addition in order to conceptualize the transitive closure in a more efficient manner. If you like this video, go ahead and click on the like button. If you like the videos that I'm doing here, go ahead and click subscribe. And if you got any questions or you want to just make a comment, tell me what you think, go ahead and send me a comment.